Good afternoon, everyone. Welcome to the Georgia Tech Manufacturing Institute's Lunch and Learn series. My name is Billy D. Brown. I'm a research faculty and director of manufacturing education programs for GTMI. GTMI is one of 11 interdisciplinary research institutes at Georgia Tech that uniquely focuses on manufacturing research, development, and deployment. We help tackle the grand challenges of today's manufacturers and assist partners in moving innovations from the lab to the market. GTMI has a wide variety of facilities and equipment located on main campus for basic research and nearby on 14th Street for more applied research in our advanced manufacturing pilot facility. GTMI's mission includes education and workforce training, collaborative partnerships with industry, academia, and government, as well as thought leadership. GTMI hosts a Lunch and Learn series each semester. This spring, sessions will be held every Monday at 12 p.m. noon as live online events. Today actually is an exception. We're going to have a pre-recorded lecture today from one of our international partners at the National Singapore University. And that's largely due to the time difference. So the sessions that we present for our seminar series are excellent opportunities for Georgia Tech faculty, undergraduate and graduate level students and researchers, as well as a global manufacturing community to learn and share advanced manufacturing knowledge. To ensure a smooth presentation experience, all audience members are automatically muted. Because this is a pre-recorded lecture, if you have questions for the speaker, I'm actually going to give you his email address. So you can email the speaker. His email actually is starts with the letter A, and Senthil, SENTHIL @nus.edu.sg. I'll provide the email address again at the end of the presentation. Today, I'm pleased to introduce Professor Senthil Kumar, who will discuss ultra-precision machining of optical surfaces. Dr. Senthil Kumar is an associate professor of mechanical engineering at the National University of Singapore. His expertise is in manufacturing with a focus on ultra-precision machining, hybrid machining of micro nanostructures, and fixture design. He has co-authored 2 books in fixture design and has published over 150 technical papers in international journals. He's in the editorial board of the Journal of Manufacturing Processes, USA, Journal of Micromanufacturing, Nanotechnology and Precision Engineering, and International Journal of Materials, Manufacturing and Optimization. He is the recipient of several awards, including the Outstanding Young Manufacturing Engineering Award and IES Prestigious Engineering Achievement Award from the Institute of Engineers, Singapore. He's a member of IIE, ASME, and he has 2 patents to his credit and has licensed the technology to start a spin-off company called Microtools, which specializes in manufacturing of ultra-precision machining tools. In today's session, Dr. Kumar will discuss the recent advances on diamond turning of optical molds. This talk will also focus on the ultra-precision machining of functional microstructures on roller molds for roll-to-roll manufacturing of optical film, and machining of optical molds made from difficult-to-cut materials, non-diamond turnable materials and brittle materials for injection molding of plastic optical components. Several technological innovations developed will also be discussed in the presentation.
Hi, good afternoon. Welcome to this talk on ultra-precision machining of optical surfaces. I'm Senthil Kumar. I come from the Department of Mechanical Engineering at the National University of Singapore. Before I go into the details of the research that we do, I would like to share with you some of the machine tools that we have in our facility, which we use extensively for making these optical surfaces. We have a Toshiba ULG 100, which is a 2-axis ultra-precision machine. We also have more nanotech which is about which is also which is a 5-axis machining center, and this is located at SimTech, and we collaborate extensively with SimTech. And some of the work that I'm going to present is also the work that was done together with SimTech. And we also have a in-house built ultra precision lathe, which is UPL 420, which is again 2-axis, and it has a fast spool servo attached to it. We also have a DT110, which is a multi-process machine tool, which has the capability to do EDM. We have the capability to do milling and drilling on the same machine tool. So we actually use these machines for making very fine features. And on top of this, we also have the following machine, or the machines specifically for characterizing the surfaces that we machine. First, of course, we have a Taylor Hobson stylus profilometer. We have a white light interferometer, Mitutoyo. We have scanning electron microscope. We have Alicona 3D microscope, and we have Kien's digital microscope. So these are some of the equipments that we have in our facility that we actually use to machine and characterize the machined optical surfaces. As an outline, I would like to give you a brief introduction about the ultra precision machining. I'll also go into functional optics on inserts, how we make them, especially using compound diamond machining and diamond microlithography. And I will also talk about the functional optics on roller mold. I will also move on with the Gravure roller, linear Frontal Lens, and how radial Frontal lenses are machined. And I will summarize my presentation with a brief outline of what we have been doing. Okay? As an introduction to go about the ultra precision machine tools, we have what is shown on the left here is basically the kind of a the Moore machine tool having the 5-axis. Basically, we have an x-axis, y-axis, and the z-axis. X and z are horizontally placed, y is vertically placed, and we have a c-axis mounted on the y, and the b-axis is mounted on the z-axis. Okay, so when you want to make complex surfaces, all the 5 axes will be activated in order to produce very interesting features. We will also be seeing how on top of these 5 axes, we also add additional axes in order to produce very interesting features as well. As we move on, we will be sharing some information on that as well. Okay. So when we talk about ultra precision machining, we would like to see a surface roughness below 10 nanometer. Ideally speaking, okay, and of course, an acceptable range would definitely be below 10, but in some instances, people go for 20 nanometer as well for surface roughness. But the machine capability should be extremely good, having a very high resolution of 1 nanometer and so on. Okay, therefore, we can actually produce a very good quality surface using these kind of machines. So when we talk about the functional optical surfaces, generally our interest is to make a hybrid freeform surface. So what do you mean by hybrid freeform surface? Basically, hybrid freeform surface actually is an integration of multiple freeform surface in order to produce very interesting optical surfaces, having higher performance capability, and also to provide new optical functions. The basic task is how do we produce the toolpath for this in order to machine them. Like for example, what you see is a sinusoidal flat, wave on a flat surface, and you have a parabolic surface. And how are we going to combine these two in order to produce interesting features? So that kind of combination actually yields very interesting novel surfaces. They are called the hybrid freeform surfaces. Now, where are these surfaces used? Okay. Some of the examples of these hybrid freeform surfaces are shown here, where you actually see that people use the Frontal Lens based concentrators on top of solar cells in order to increase the efficiency of capturing the light efficiently onto the solar cell. People use it for making collimators, also in the detecting blind spots as well in the in the cars. People actually have these kind of special mirrors which are made. They are also, freeform surfaces. When we talk about optical freeform surfaces, naturally the first thing that comes in the mind is the lens. Generally, when it comes to digital camera, people use different types of lenses, and some of them are shown below. These lenses are very big to extremely small, like as you see today in the mobile phones, as well as in the at the back of the mobile phone, having frontal lens made for flashlights to throw the light for a very long distance. People use these kind of lenses. Also, we have these lenses used in imaging devices. People use it for capturing images. Also in automotive industries, where the headlights are made with special lenses, so that the headlight, whatever that is coming out, is also thrown for a long distance as well. People also use it in LEDs and so on. So there is a very wide application of these functional optical surfaces currently in the industry. Also, this is another interesting example where you actually see an ultra short throw projector. As what you see on the left hand side, there is a projector that is placed very close to the wall. The distance between the wall and the projector is only 46 centimeters. You actually see that the projector has a very interesting mirror or a lens placed on top, which is actually used to throw the light onto the wall. So there are a lot of interest in such devices that are coming up in the industry. Also, you see that these kind of special mirrors are used in making movies, especially in the movie Sleeplessness in New York. It was shot with the help of a very interesting freeform mirror. That is what is shown in the image as well here. So these are all actually just to give you an overview of different types of functional optical surfaces that people use. But there are also a lot of interest today in making very interesting, intricate features, how we go about machining them or making them. So in order to achieve this, we use something called as a compound diamond machining. So what is this compound diamond machining? Primarily, this uses a diamond turning. Basically, we use a diamond as a tool for cutting. And in this case, we use special tools. Like, for example, we use a fast tool servo, FTS, we call it in short. We have a slow slide servo. Also, we have diamond milling and raster fly cutting. These are different types of processes that people use in order to produce these interesting features. When we talk about the fast tool servo diamond turning, the biggest advantage is that it's a very high bandwidth servo, which has a frequency which is more than 10 kilohertz. Whereas the problem is that it has a very short working depth, which is less than 1 millimeter. And that too, it depends on the actuator or the type of actuators. For example, if you use a piezo actuator, the travel length is much less, in the order of tens of microns maximum. In the case of slow slide diamond turning, the advantage is that it has a long working depth, but it has a low bandwidth servo, which is less than 1 kilohertz. So you can actually see that fast tool servo and slow slide servo complements each other in the process. So one of the things is that if we can actually combine these two, we will be able to achieve better quality features. That's one thought. And people use diamond milling as well. It has a greater flexibility, but however, the biggest problem is the low material removal rate, and especially much less compared to the turning process. If you use the raster fly cutting, we also understand that large scale production, it is very good for it. However, it takes a long setup time, and there is a restrictions in the tool swing diameter as well. So on the bottom, actually, you see an image which shows the complexity and the dimensions of the structures. For example, if you use diamond turning, the functional element, which is in the range of 1 micron to 1 mm. So it is quite a big range. People use it for making Fresnel lens, of course, diamond milling for gratings, in some cases for triangular reflectors, slow slide for freeform. We have fast tool servo for faceted mirrors. We do have, diamond micro chiseling for corner cubes and so on. But there is always more innovations come up on different structures. So the challenges are also posed on to the people like us who do machining on for generating ultra precision surfaces. So therefore, we have to develop novel diamond turning techniques in order to produce it. So hybrid and compound process is needed in order to address the challenges in the machining of highly complex structures accurately at higher material removal rates. So this is extremely important because conventionally when we use ultra precision machining for making lenses, most likely it may take days to machine. Whereas the interest in the industry is to speed up the machining process as well. So there are a lot of interest in having a higher material removal rate into this process. So what are these hybrid compound systems? Primarily, we have the aspherical convex and concave surfaces. Maybe either they could be spherical or aspherical. We have prismatic convex and concave surfaces, creating very interesting features as shown in the image on top, where you can actually see that there are different types of features that are produced, either be it a linear feature or a curved feature and so on. Okay, these can be generated by turning process, as what is shown below on the left hand side. You actually see by using the turning process, you can actually produce very interesting shapes using profile turning. We can also use form turning in order to produce interesting features. We also do face milling to make spherical or aspherical concave and convex surfaces. We also have, we use fly cutting or peripheral milling to produce micro grooves or intersection of micro grooves in order to create prisms or any other features associated with that. So what are the challenges that are there? There are primarily a few challenges. The first one is in the case of, say, fly cutting, we can actually produce very good features, but unfortunately, we cannot produce really a very sharp corner. As shown in the image here, you will actually see that there is a small kind of a projection that goes on both sides. Under the fly cutting, you can actually see that the surface actually has some form of the grooves actually extend on either side. When it comes to micro grooving, you actually see the groove is extending on one side. If you use face milling, the sharp corner is not produced. However, you get a very nice curved surface. However, if the industry need is primarily to focus on really sharp corners, they like to see how we can actually make perfect sharp corners. So the challenge was posed, and we had to develop some innovative processes to come up with that by combining, if it is possible, with the combination of fast tool servo and slow slide servo to produce it. So that is what is a challenging challenging task. So we went on to explore. Actually what you see here is on the left hand side is a fast tool servo, where you can actually see the cutting tool is moving at a very high frequency, moving forward and backward. And at the same time, on a slow slide servo, you actually see that the cutting tool is moving very slowly, but the distance that it moves is greater, and it can move very slowly to cut the surface. So we actually mount the workpiece on a Z-axis, and we mount the fast tool servo on the Y or the W axis in this case, okay, which is superimposed on top of the Z axis, so that it can actually go into machine very complex and intricate features. So one of the example of these kind of surface is actually a multiple compound eye surface. Basically, the compound eye is shown on the left hand side. What happens is that this has a spherical surface, multiple spherical surfaces, and on top of the multiple spherical surfaces, we have much smaller spherical surfaces. Okay, so how do we go about doing it? So what we do is we generate the tool trajectories for hybrid freeform surface, having multiple frequencies in this case. They can be simplified and split using hybrid Hilbert transform and the fast Fourier transform approach. For the image, basically from what we can see is that the desired frequencies are about 6.063 and 47.03 Hertz. So these frequencies can be represented as degrees of curvature in the freeform features. Therefore, we are able to split them into two freeform surfaces, as shown in the picture here, where you see an SSS process produced with multiple, spherical, lenses, and then also we have the application of fast tool servo with again multiple freeform surfaces of much smaller, the lenses. So these freeform surfaces with lower frequency and with a sag of height of about 0.3 mm can be realized by slow slide servo, while the higher order frequency having a sag height of about 15 micron can be handled by the fast tool servo. So by combining this, we are able to increase the spindle speed to 50 RPM. By increasing the spindle speed, we also see that the quality of the surface that is produced is also very good. So we are able to actually achieve better quality surfaces and at the same time improve the production rate, or the material removal rate is increased. And at the same time, we also see that we are able to produce these intricate complex surfaces on, using the combination of both the slow slide servo and the fast tool servo together. So when we do this process, we actually observe that, the machined surface is also equally good. The photographic image of the fabricated multiple compound eye is actually shown at the bottom, where you can actually see that, on top of the spherical surface, we actually produce the micro features as well. So this is one of the very interesting study we did. This is again one of the requests by an optics company that was interested in making very interesting lenses. So we actually did this machining for them. And this is another work that we did on actually using slow slide servo and the micro grooving technique. Actually, what you see is that the slow slide servo is able to move further in terms of greater distance it can travel. And we use the micro grooving technique in order to produce very interesting features as well. The kinematics of this is actually shown here in the image, where you actually see that the cutting tool is in one particular direction, while the angle or the rotary angle is kept constant in order to actually produce the desired feature there. So let's say, for example, if we are actually required to machine a very complex surface like what I show here on the left-hand side, which is a hexagonal Fresnel lens design. So in this case, machining of this freeform surface is done using the in-house developed Guilloche machining technique. This technique employs the X, Y, Z axis and one rotational axis as well. In contrast to the conventional ultra-precision machining techniques, the diamond tool tip is considered as a fixed point on a big circle with radius R, and the cutting action takes place around the small circle at radius rho in this case, and the tool trajectory permits the tool to cut the workpiece in a direction tangential to the small circle. Which is similar to that of face turning. So in this case, we try to control that. And because of this, the chip always flows towards the tool rake face. And two conditions arise from here to determine the tool trajectory. And based on this, we can arrive at the control points, basically the exact points where the cutting tool has to be there, and so as to machine this polygonal Fresnel lens. So using this technique, we are able to actually machine very interesting features as well. So when we combine this, basically the most critical thing is the sharp corners. So at these sharp corners, we have to negotiate them by actually rotating the diamond tool in relation to the surface that we want to machine. So what you see here is a combination of these multiple, hexagonal Fresnel lens. They are successfully generated tool trajectories are actually shown here in this example. As an example, the cutting points are mapped onto the central and the offset Fresnel lens. The simulated tool path is shown below, where you actually see to cut the central Fresnel lens, the tool path is what is shown here. Okay, this is the tool path, and for machining the off-centered one, the tool path is what is shown here. Okay, all right. So interestingly, the toolpath is very unique in design, and using this technique, we are able to machine very interesting features as well. So the machined frontal lens, which is hexagonal lens, is actually shown here. This is used for solar cell concentrators, where the gap between the lenses are completely eliminated with the use of these hexagonal lenses. Okay, so now we move on to the next area where we focus on the grayscale pixelated micro images on metal surfaces. So our aim is how do we machine on metal surfaces where we can actually produce very interesting features on the surface. Okay. So why do we need to focus on this? Basically, there is a lot of interest in this area of anti-counterfeiting. Basically, because counterfeiting products have been a persistent problem in the industry, and basically they having counterfeit actually discourages innovative efforts and cause direct economic loss to the original manufacturers. So there are a lot of interest in anti-counterfeiting. They are basically necessary to protect the intellectual property and the manufacturing originality. As an effective method in anti-counterfeiting, micro images have been used or utilized, especially in the case of dollar bills. People use in gold coins, as well as in papers and plastic materials as well. Although printing technology can be used to easily transfer images onto the plastics and onto the papers, pigments have to be used in the manufacturing process, which is not desirable for quite a variety of products, and also has limitations on the smallest image size again. Okay, and here we explore how machining techniques can be used to produce visually distinguishable features. So that is our goal in this particular study as well. So grayscale digital images varies from basically what happens is that grayscale digital images basically varies from black at the weakest intensity to white at the strongest. When a micro image is being generated on a metal surface, a concave feature can be machined to produce a different level of luminance to represent the level of darkness of each pixel. Compared to the unmachined zones without any feature, the light rays illuminate at the machined concave feature are diverted to other directions instead of being reflected back to the observer. This could result in a relatively lower luminance level perceived at the concave zones. Basically, to achieve the visual effect, an inverted pyramid is considered, as it has a simple symmetrical geometry with squarish aperture. So this inverted pyramid cells can be used as a function as the pixel of the micro image, where each cell suppresses the luminance perceived by the observer at the reception location. So the cells will appear to be dark to human eye due to the deviated light reflection compared to the unmachined zone, which appears to be bright. Ideally, both the engraved cell and the flat unengraved surface should have a mirror-like surface finish in order to realize this. But without this, it is impossible to produce that. An example is actually shown here, where you see on the right-hand side, where you have multiple series of concentric rings are produced by just creating these dots on the metal surface. So depending on the size, which is the D, the distance D, which is the aperture D, the size, as the aperture size increases, it becomes much more darker. While the aperture size decreases, when the D is smaller, it becomes more brighter. At the same time, the angle of the aperture also matters, or the inverted pyramid, the angle of the pyramid also matters. The bigger the angle, the brighter it is. So there can be an optimal angle that we can also arrive with the combination of d and the theta in order to produce very interesting features that we want. Another example of, so how do we go about doing it? Basically, we need to produce these very interesting images. So what is the technique to do it? So we actually use the spiral tool trajectory and the grayscale image. Basically, we superimpose them in order to produce the feature size and the aspect ratio. So using the diamond microlithographic technique that we have developed, we are able to machine these features. For example, the image of Einstein is shown, which is in grayscale on the top left-hand corner, and that is actually transformed into the tool path by superimposing the spiral tool trajectory together with the grayscale image. And with this combination, we are able to actually identify the aperture values and the depth that is required. So what we actually see is that from the machined surface, you are able to actually see a very interesting, very clearly visible image. What you see on the right-hand side bottom is actually a machined machined image, where you actually see the machined marks as well. And all this complete image is produced by means of chiseling, where you make micro dots on the surface, which is similar to that what is shown on the left-hand side. By characterizing the feature size and the aspect ratio, we are able to determine, depending on the grayscale value, what should be the aperture size and the depth, and we are able to produce the image like this. You can easily see how good the quality of the image is, especially the hair. Even the hair is all clearly visible in this particular image. So we are able to produce very interesting features out of this technique. So having developed this technique, we wanted to explore and see at different tool geometries how the image behaves, and we want to have an understanding of the whole process in this. So the resolution of both the images, basically what you see at the top is 430 by 560 with a total number of pixels about 240,000 pixels there. Okay, approximately about 240,000. So a distinct difference in the contrast level between the two images are seen here in this particular image. Basically, the darker and the sharper pixel are found to be at the corresponding locations for micro images to be machined using the tool 1 compared to that of tool 2. Basically, when you use tool 1, you see a better image, while in tool 2, the image is not of good clarity. That is obviously seen in this. And the quantitative analysis of the grayness distribution in the figure below leads to the same observation of more dark pixels present in the micro image as well, which can be seen at the bottom graph, where you actually see more red color or dark pixel is observed in the red color column. So these experimental results corresponds to to the simulation as well. So we did some kind of a simulation earlier in order to also understand how this will behave using these kind of tools, and then it actually matches very well with that. And using this, we can conclude that by controlling the tool angle and the depth, we are able to produce very sharp images as well. Okay, so what we did is we went on to continue the study further to explore, how the size of the image, matters in this particular instance. For example, when the size is 2 mm, which is at the bottom, where you can see that the entire size of the image is 2 mm, we can actually see the image very clearly in the naked eye. Whereas when the size is 100 micron, it actually is seen as a black tiny mark on a brass workpiece. With the assistance of optical microscope, all the images are recognizable. Relatively, poor in terms of when the R is very, very small. Okay, so the resolution and the quality of the image can be improved by introducing smaller engraved cells or individual pixels in this case. The machining time of these images are about 320 minutes for R of 2 mm, whereas 21 minutes for an R of 100 micron. So you can actually see that there is a considerable decrease in the time when the image, entire image size is also smaller. But you also see that the quality of the image also deteriorates poorly, or rather becomes bad when the size becomes very, very small. Right. So using this technique, we are able to actually produce images on, or any grayscale image that you give on metallic mirrors, which can be formed as a mold to produce whatever the surface, the features that you want on the devices to go in for anti-counterfeiting and so on. So we move on to the optical molds. How do we make them? Basically we want to make the optical features on roller mold. Primarily the reason is because we want to use the techniques that we have earlier developed, primarily on the diamond chiseling, where the Einstein picture was produced, and we want to use it onto a roller mold in order to produce functional applications as well. So this is one facility that is available at SimTech, where we actually collaborate extensively, where you see the roll-to-roll facility shown here. We have the thin film, which is a polymer film, and we have a roller mold here. And the roller mold has the pattern, which is actually printed on top. And this is what is actually the printed sheet, which shows the different features that are present here. And SimTech has also, actually made the LEDs on this thin sheet of material using the roll-to-roll embossing technique. So basically, a roller mold consists of the main high precision roller mold at the center, which is A, and we have two smaller rollers, B1 and B2, that is just to create the tension so that the film actually can pass through it. And the bottom one is basically where the ink is placed, and the ink actually copies from the mold onto the polymeric film, so that we can actually produce whatever pattern that we want, which actually passes through a dryer so that it dries off, and then we can produce the functional features on the polymer. So how do we go about doing it? And this is roller mold is made with 3 different techniques. People use the Gravure roller mold. That is one technique. I'll also be explaining where we use this Gravure roller mold. There is also one more, which is the linear Frontal Lens on a roller mold. We also will talk about the radial Frontal Lens on the roller mold. So these different techniques that can be used in order to produce very interesting features on the molds, and which can be replicated onto a polymer or any polymeric film. Now, this Gravure roller for roll-to-roll printing of metal grid has become very important. The main reason why this has become an interest in the industry is also because of the application of this rare material, which is called as the indium tin oxide, which is present only in very few countries in the world. And this indium tin oxide is primarily used in touch screens. In most of the mobile phones, and all the touchscreen pads that use consists of this basically a transparent conductive film made up of indium tin oxide. So the industry interest is to actually develop techniques in order to remove this indium tin oxide. Primarily it's ITO free transparent conductive film is their interest. So how do we go about doing it? One is by means of metal grid, or people use the silver nanowires, conductive polymers, and carbon nanotubes. So what we thought is, why don't we use metal grids and use the chiseling technique that we have developed, and implement the chiseling technique on top of this rollers mold in order to create these kind of thin lines, which can be used for conductive, which will make any thin film to be a conductive thin film, because these thin wires or metal wires, we can actually use it to study the conductivities and so on. So we wanted to explore this opportunity. Okay, so we went on to use the fabricate the Gravure roller mold. Primarily in the industry, people use laser engraving in this. People also use electrochemical and electromechanical systems. Also, people use chemical etching. These are some of the companies that are very specialized in this. People actually make very fine, very intricate features. But the only thing is that they are able to machine cell size, that means individual pixel, about 25 micron in size. And when you make these cells, which are about 25 micron, the printed line width after you pass through the ink, which will be about 50 microns, okay, which is relatively thick. And when you have 50 micron thin, 50 micron thick wire, you are on a transparent surface, you actually see that the transparency decreases significantly. So our aim is to reduce the width of these cell size, and therefore we can in turn reduce the printed line width as well. So this indium tin oxide free alternative, made a very interesting study as well. In other words, that it actually triggered the interest in order to make very fine, intricate, chiseling. So we went on to machine them on the roller mold. Simply, we wanted to create these patterns. The pattern is shown on the right hand top here. Individual cell is primarily a very small portion, and after you print it and pass through the ink, you will end up getting lines continuously like this. These individual cells are placed with a small gap in between, but after it passes through the ink, a constant steady line is actually produced or observed in this entire process. So how do we go about doing it? The gravure printed roller mold is at the bottom here, and the ink is at the bottom, where the mold rotates through the ink, and then the ink is carried on and then impressed onto this impression roller, where you see a very thin film substrate that passes through this impression roller, which is again cured on the other side and then rolled back again. Okay, so this entire process basically transforms the ink from into this from the pockets or the small holes into some kind of an elliptical line being produced. When it is cured, it forms they merge together to form a very thin line. Okay, so we went on to explore this, and the industry currently is using the laser engraving and the electromechanical engraving and chemical etching. But we wanted to see how we can replace this with a different methodology, and that is where this gravure roller machining comes into play. So this is the roller where you have the micro lines that are being drawn out, and these lines, individual lines, consist of hundreds of pixels, and these pixels have a very small gap here, and the ink actually is placed inside this these pixels. And actually, once they are placed and printed onto the plastic material, you actually see a very continuous line being produced. Okay, and that is what is observed at the bottom here, which is shown in this image. So how do we go about doing it? And this is done with the help of a diamond micro engraving technique, which I mentioned to you earlier, where when we wanted to machine the Einstein image, we actually did the same process to do it. And what you see here on the image at the bottom, where there is a video where you can actually see the cutting tool is moving forward and backward in order to create this kind of a diamond micro engraving. So in this case, you will actually see that the micro engraving is happening because of the technique. How this happens is that the cutting tool enters here in the beginning, goes down all the way, and then it is chiseled out by moving away, and then you can produce a very interesting kind of a V, kind of a pyramid structure being produced. Okay, so here we control the D, that is the distance, the opening of the aperture, as well as the depth, in order to accumulate or hold the ink in this particular instance. Okay, so what we can also do is that we observed that some burrs are being formed, and how we can overcome the burr is by creating a small tilt in the angle, and by doing so we are able to create a very interesting feature without any burrs on the surface. Okay. Likewise, when we continue on, we are able to actually use the slow slide and the fast tool servo combined together in order to produce these micro grooves. And with this, we are able to see a gravure roller being machined, and each roller consists of hundreds of lines like that, and each line has hundreds of dots, and one of the dot is as shown here in this image, where you see multiple dots are placed, and if you zoom just one particular dot, and that is something like this, where you can see that the average length in this case is about 10 microns in this particular image. Okay. So in the industry, there has been interest, and a lot of people are moving in this direction to make these very fine features. People have done it with 25 micron, 7.5 micron and 5 micron using electromechanical engraving technique. People have done it. So we went on to machine. Initially, we machined a very big cell, which is about 32 microns, and then we moved down steadily, and then we were able to achieve line width of 2.7 micron, and which is when you print it, the line length is about line width is about 3 micron after printing, which is a significant reduction compared to that of 5 micron, which is the industry standard today. Okay, so with this technique, we are able to produce very interesting, very fine, small, dots, which can be filled with ink in order to reproduce it on the flat screen, so that you can produce a very, interesting line with which has the facility to do the conductivity and so on. Okay. So roll-to-roll printing resulted in some problems as well. There are some discontinuity in the printed lines as well. It is observed, and that is also because of the ink transfer. Also, in some instances, too much ink is transferred, and so we need to still optimize this process so that we can achieve a better quality features as well. So Greview printing using engraved roller molds actually tried to reduce from 25 micron cell width to 10 micron. And we also observed that the line width also gets reduced from 47 to 19 micron, which is a significant reduction in the line width as well. And in this case, consistently we can see very good quality. Although the transmittance is not as good as that of ITO, still there are some improvements need to be done. If a good improvement can be made, probably in due course we will be able to replace the ITOs as well. Okay, meaning the indium tin oxide based touch screens can be replaced with metal oxide based wires, which can actually help in increasing the conductivity and thereby the the touch capability as well. So this next we move on to the linear frontal lens on a roller mold. Primarily, again, this is interest because of the solar cell. People wanted to actually mount this panel on top of the solar cell so that the concentration of the light can be realized, and then the efficiency of the solar cell can be increased. So how do we go about doing it? Primarily, in this case, you actually see that the spherical lens, which is shown here, can be converted into a Fresnel lens. Okay, this is one. Or we can use the other way around, wherein we place the light source and allow the light to travel a long distance, as in the case of a lighthouse or in the case of a car headlight, where the light is at one single source. When it comes out, it is thrown out to a longer distance so that the distance traveled by the light is really relatively far. Okay. So in this case, the Fresnel lens is an example of a compact, flat optical component. It has a wide range of applications, either as a light concentrator or a collimator as well. So people use these Fresnel lens for making very interesting features. One of the classic example is behind the cell phone. You actually see that these Fresnel lenses are placed where the flashlight is, so that the light can actually travel longer distance. So how do we fabricate them? The fabrication is done by direct diamond turning. In some instances, people use plastic injection molding. Of course, the best way would be by using the roll-to-roll printing. Or in this case, is called the roll-to-roll embossing. Okay? And the biggest advantage is that it will become low cost if we do this technique. However, the cost of making the mold is high, and that has to be compensated by actually increasing the production. so that we can have a large throughput so that the cost can be significantly reduced. So the lens design is made by considering two factors. One is the equal height, where the height of the lens is constant, as what you see on the image here. Also, on the other side is where the equal width on the frontal lens is also observed. So either we have equal height or equal width in order to produce the these kind of frontal lens. But if we make equal width, the problem is that the height of the frontal lens varies, and that is actually very difficult in some instances to machine. So we prefer to go in for equal height. Of course, depending on the application, some may want different combinations of this height and the width for different types of lenses and so on. So what you see here is actually a toolpath generation for this particular workpiece, where you actually see on the left side is basically the tool is actually moving from the center towards the outer, and as it progresses, you also observe that when the cutting tool, when the workpiece starts rotating, the cutting tool also starts rotating about its axis. Therefore, it is able to actually machine very complex surfaces as well. What we see here is actually the machining and the characterization of the machined lenses. Primarily, we have to measure the left section of the profile and the right section of the profile, and that is what is actually shown in this particular image here, where you actually see that the left section of the profile having features like this, and which is observed at the bottom, where the extreme left is very sharp, and as it progresses inside, the angle is deeper, and you can actually see the central feature, which is a spherical lens being produced. And of course, we use the stylus profilometer in order to measure this. However, this is not a very good way to do it because scratches will be observed, but for a study purpose, we did it. So it is just for our investigation only. So you actually see that the deviation of the error from the designed profile is actually shown at the bottom, where you see the left section and the right section does not deviate too much from the 0, which is, if at all it deviates, it's much less than 0.1 degree. Okay, so which is very within the acceptable limits. So then what we do is after we do the machining, we do the embossed film for quality purpose. So this is the roll-to-roll embossing system, where you have the roller which is machined, and you have the guide rollers at the either side, and the PET film runs through the roller, and at the bottom is where the UV lamp is there to cure it. Okay, so people have used this technique in order to produce these long LED PET films. And we also do characterization of the Fresnel lens by using, again, measurements. After we do the PET, we also do the measurements using the stylus profilometer to see the deviation of these angles. And what you see here is actually the actual measurement, which is less than 1 degree. And also we do some optical performance evaluation, and we see how the concentration of these lenses using the super solar simulator. Then we actually use the cameras to detect phase at the focal point and then see how the intensity is. And of course, you observe that the intensity is relatively very, very high compared to that of a normal flat film. Okay, so it has a definite improvement in terms of the application. So we actually use these techniques in our for machining and actually for industrial applications as well. So the radial Fresnel lens on roller mold for roll-to-roll embossing is something which is very important to us because now we are directly machining the Fresnel lens on top of a roller and then use that roller for embossing purpose. Therefore, we are able to produce long, continuous these Fresnel lenses on polymeric films. So basically, the research challenge is basically you have lenses. Generally, people make a lens design, then they go for diamond turning or flat mastered mold. Then they do electroplating, basically electroless nickel, and then of course they wrap around this plate onto the drum and then use it for roll-to-roll printing. However, if we do this, the accuracy and the quality is significantly dropped because it has to be fixed on the round roller. The quality of the feature that is produced is not good. Therefore, we are actually interested in replacing this particular technique and directly machining the Fresnel lens on the roller. If we can achieve it, our quality of the part that we produce will be significantly increased. So in this case, we actually do the lens design initially by means of some CAD model, and then do some simulation, and then we directly machine them by generating the tool path associated with that in order to make these Fresnel lens, and then we do the testing on that. Okay. So in this case, if you notice it, you will actually see that when the cutting tool is moving in, there are some cutting edges which are very difficult to machine, especially this dark patch here is quite difficult to machine. Therefore, what we need to do is that if we can actually make a very small adjustments to the cutting tool, the angle of the cutting tool can be made in such a way that it can actually penetrate into those zones for cutting the material. Okay, so we actually mount devices on top of the existing C or the B axis in order to make these fine adjustments, and that is actually done with the help of goniometer. So we actually mount a goniometer on top of the B or the C axis and then make the cutting tool to adjust so that the dark zone here can be also machined by varying the tool angle. So in this case, what happens is that we are trying to simulate or create a geometric relationship between the tool and the workpiece in relation to the arbitrary points by synchronizing the tool and the roller rotating process. So in the machining process, C and the Z axis are programmed to perform the kind of a rotary motion between the roller surface and the tool tip, and achieve the turning process. So by continuously using the B axis in synchronization with the C axis, and to ensure the constant cutting angle between the tool and the roller surface can be achieved, we ensure that the depth of cut in the machining process is realized by the Y movement. Okay, so that by synchronizing the movement of C and the B, we are able to achieve the necessary features, and also the depth is realized by the Y axis movement. Okay. So by this process, we are able to achieve machining of very complicated features on roller molds. So the bottom simulation actually shows how the tool and the workpiece will rotate in sync in order to produce that kind of feature. However, the biggest problem that we see is that after we do the machining is the measurements. Okay. So we need to actually compensate for because the roller, when it is placed horizontally, it may not be horizontal, and the quality of the feature that you do by scribing may not be also accurate. Therefore, a lot of simulations have to be done in order to realize that, and then we do multiple measurements and compensate them for inclination by changing the angle and so on, and then we arrive at the actual profile that is there, and then we create or construct a 3D model. Okay, and that is what is shown on the top here. Okay, so how do we go about doing this machining? So the first is the roller mold. So the roller is placed, and the tool is set using the tool setting here, where the tool is mounted, and we have the rotating diamond tool for making the Fresnel lens. Actually, you can see the cutting tool is at this particular point. And we have the Fresnel lens, which is basically the linear Fresnel lens is produced, which are normally the lines or the grooves. And then the stylus profilometer is used for measuring it. So this is actually the different types of, the lenses together with, the radial lens as well as the linear Fresnel lens are produced. And then we actually directly machine it on the mold and or on the roller, and which will be used for print. Okay. After we make it, we also do diamond-like coating on the lenses, especially on the roller. This is to prevent the wear, and then we can use it for a longer duration of time. And we will just mount it, and then we can produce these kind of interesting lenses which are observed on the right hand side here. Okay, so this is actually the image at the end of the day. This is the lens which is on the top. When the light passes through, you actually see two white lines and then the dots at the center. So basically, in this particular instance, what happens is that there are situations where when the rotating tool dynamometer has a round nose, it ends up creating unmachined features or unmachined zones. And this is because of the the contact of the tool and the workpiece. So what we try to do is that we actually create a swinging, rotating diamond shaping technique where this edge is kind of adjusted so that we can actually produce very deep features out of it. And this tool swings a very small angle so that as shown here, and you can actually achieve the greater depth till the point where we need to create a very sharp corner. To evaluate the proposed swinging, rotating process, an array of frontal lens with 4 different feature heights are firstly machined on the roller mold, and different lens height design will lead to different number of rings as well as the different width and size of each prism. So in the proposed shaping process, as the straight profile is directly formed by side cutting edge in one revolution, it is believed that the length of the profile may affect the generated surface quality. From the 4 images shown, the reflectivity of the machined lens, you can clearly observe that the surface quality of the machined lens becomes worse with the increase of feature height. We then put the machined lens under the confocal microscope, and you will see a very obvious irregular chatter marks on the machined prism. The measured surface roughness using the surface profilometer also shows a similar trend on the variation of the surface quality, which we believe is associated with the width of the prism. According to a preliminary simulation on the shaping of one prism ring, we can observe that the simulated cutting force for shaping revolution also increases accordingly with the increase in feature height, which possibly accounts for worse surface finish after the shaping process. The main objective of this study is to enhance the efficiency of the frontal lens cutting on roller mold. So it is necessary to evaluate the capability of efficiency improvement for the proposed SDS method, which is the swinging method. If the previously proposed rotating diamond tool process is utilized, the machine to machine a 90 mm lens, as shown in the slide, you will see that it takes about 21 days to do it. Whereas when we use this swinging, it is only 0.7 days. So there is a significant reduction in the hours. So we actually improve the material removal rate using this process. Okay. So this is there is a significant reduction in the machining time. This is due to the enhanced material removal rate of the proposed shaping process. In the RTD process, very limited chip volume is removed in each cutting revolution due to the tiny nose tip that is used to cut the workpiece and form the profile. While in SDS process, the side cutting edge is used to directly form the straight profile, and the uncut chip volume increases accordingly when the tool feeding along the height direction. So obviously also you see that there is a slight reduction in the quality of the surface roughness just because the material removal rate is high, you also see that the surface roughness for the rotating tool, even though it takes about 21 days, the surface quality is about 6 to 10 nanometer. While in the case of swinging, you will see the surface roughness is about 7 to 17 nanometer. Okay, in summary, what we have done so far covered is basically the ultra precision machining of functional optics on inserts. We also looked at how the ultra precision machining of complex frontal lens can be machined directly on rollers, and how we can use that for printing as well. Okay, so this covers the my presentation, and so in this particular study, we also looked at the direct cutting of frontal lens on the roller mold. Primarily the rotating tool diamond turning initially we developed, where the lens diameter was 10 mm, and then we went on to the embossing process as well, where the lens diameter was about 30 mm we did, and then with the swinging rotating diamond shaping, we made a lens with about 90 mm in diameter. Okay, so we have machined different types of lenses, and different types of techniques have been developed, and the modifications on the machine tools were made in order to realize complex surfaces. Several works reported here are not possible without the support of the following PhD students and external collaborators: Dennis Niu, Huang Rui, and Xin Chuan. All of them are my PhD students, and of course with the support of Dr. Liu Gui, who is a scientist at SimTech. And you can reach me at mpeask@nus.edu.sg or asenthil@nus.edu.sg, and I would be happy to interact with you. And if you have any questions, I'll be happy to answer as well. Thank you all for listening to this, and I'll get back to you if you have any queries. Please do email me. Thank you.
Right. I want to definitely thank you guys for hanging around. This was a little bit longer. The pre-recording was a bit longer, but we thank Dr. Kumar for this detailed, very thorough presentation, and I thank the audience for your time. As you saw at the end of the presentation, there was an email address there, so if you have questions for Dr. Kumar, please use the email address that was provided, and I can certainly provide it to you as well. And if you want to send me questions, I can forward it to the speaker as well. My email address is billyd.brown@gatech.edu. And I've put Dr. Kumar's email address in the Q&A panel. I'm not sure if you can see that, but again, you can email me and I can forward the questions to Dr. Kumar. So thanks, everyone. I guess I did also put in the Q&A panel a link to the previous recordings for this semester, as well as the previous semester of our lectures. And so the link for that is just research.gatech.edu/manufacturing/past lectures. And so most of the recordings are available to you. So next week we'll have Professor Aaron Stebner. He'll be who's a assistant professor here at Georgia Tech, and he'll be presenting on machine learning for metal additive manufacturing. So that should be a very exciting seminar as well. So please join us next week. And thank you again. You guys have a great Monday.